Imagine for a moment that you are floating. You are perfectly weightless, perfectly still, in the deepest, softest darkness you have ever known. There is no sound here, only a profound and gentle silence. And as your eyes adjust, you begin to see them. Not just one or two, but countless points of light, scattered like fine diamond dust across an endless velvet curtain. This is the view from home. This is our night sky, and from this quiet, familiar place, let us begin a journey. Not a journey of speed or noise, but one of slow, wondering thought. Let us drift together with a gentle curiosity and ask a simple, spacious question. What lies above our solar system, and what, in the grand scheme of things, could possibly lie below it? To start, we need to find our footing, or rather, our floating place. So picture our solar system, not as a diagram in a book, but as a quiet, slow-moving dance in the void. At the heart of it, of course, is our sun, a warm, nurturing sphere of light and energy, holding everything in its gentle gravitational embrace. Around it, the planets trace their patient, elliptical paths. Mercury, Venus, our own Earth with its blue and white swirl, Mars, the giant Jupiter, ringed Saturn, the ice giants Uranus and Neptune. They are all there, along with moons and asteroids and comets, all moving to the same timeless rhythm. This is our immediate neighborhood. This is the realm we are beginning to know. It feels vast to us, and it is. To cross it, even in our fastest spacecraft, takes years, decades. But tonight, let us expand our sense of scale. Let us drift upward and see what lies beyond the last known orbits of our own celestial family. As we rise, so quietly, above the plane where the planets spin, we leave behind the last whispers of the solar wind. We pass the distant icy realm of the Kuiper Belt, where Pluto and its companions make their slow circuits. The sun from here is just the brightest star among many. And then we cross a threshold, a boundary that is not a wall, but a subtle shift in the balance of forces. This is the edge of the sun's dominant influence, a place called the heliopause. Here, the particles streaming from our sun finally meet the thin ancient gas that fills the space between the stars. This is the beginning of interstellar space. It is not empty. It is filled with what astronomers call the local interstellar medium, a diffuse mist of hydrogen and helium, wispy and cold, with here and there a tiny grain of dust, smaller than a particle of smoke. This is what exists in the great above of our solar system, an ocean of near-nothingness, but an ocean nonetheless. And sailing through this ocean are the other stars. From this new vantage point, we can look back and see our solar system for what it truly is, a single star system, adrift in a much greater sea. And our sun is not alone. It has neighbors. The very closest is a faint red dwarf star called Proxima Centauri. It is part of a triple star system we see as the bright point of Alpha Centauri. That light, which takes a little over 4 years to travel to our eyes, is our next-door neighbor. But next door, in a cosmic sense, is almost beyond comprehension. That distance, over 4 light years, is so immense that if we shrank the sun to the size of a grapefruit here on Earth, Proxima Centauri would be another grapefruit, over 1,000 miles away. All that space between them, that is what exists above us, a staggering volume of quiet, dark space punctuated by the lonely lights of other suns. And as we let our gaze soften, we see that these stars are not scattered randomly. They form patterns and swirls and great associations. Our Sun, along with Proxima Centauri and many others, is part of a loose cluster, a stellar stream, all moving together through the galaxy. We are, in a sense, part of a tribe of stars, born from the same cloud of gas and dust eons ago, now slowly drifting apart on their own long journeys. This is a comforting thought. Even as we voyage into the great above, we are still with family. We are part of a local flock, sailing through the interstellar medium. But the story does not end with the nearest stars. If we continue to drift outward with infinite patience, a grander shape begins to emerge from the darkness. Those thousands of stars we see from Earth, and the countless more we cannot, are gathered into a colossal spinning structure, a vast island of stars, gas, and dust, our galaxy, the Milky Way. From within, it looks like a pale river of light across our sky. But from our imagined position far above the solar system, we would see its magnificent architecture, a brilliant, bulging core of ancient stars surrounded by a great spiraling disk where newer stars like our Sun are being born. And our solar system? We are out here, in one of the spiral arms, about halfway from the brilliant center to the quiet outer edge. We orbit that galactic core once every 230 million years, a stately, slow dance we are all part of. So, above our solar system, there is the interstellar medium, there are the nearby stars, and there is the entire breathtaking wheel of our galaxy, turning with a silence that is almost musical in its grandeur. And yet, the galaxy is not the end of things. The great above stretches further still. If we could pull our perspective back, we would see that our Milky Way is also not alone. It has its own family. We are part of a small cluster of galaxies, gravitationally bound to one another, called the local group. Here lives the great Andromeda Galaxy, a spiral even larger than our own, a smudge of light in our night sky that is actually 1 trillion stars. There is the Triangulum Galaxy, and dozens of smaller dwarf galaxies, all dancing around one another in the immense blackness. This group, millions of light years across, is our immediate intergalactic neighborhood. And beyond the local group, more groups, more clusters. They gather into immense filaments and walls, the largest structures in the known universe, tracing a pattern like a cosmic web against the darkness. In the spaces between these great webs are the voids, vast, empty regions of space that can be hundreds of millions of light years across, containing almost no galaxies at all. So, when we ask what is above our solar system, the answer unfolds like an endless, gentle revelation. Above us is an ocean of near-nothingness, dotted with islands of stars. Those islands gather into archipelagos of galaxies, and those archipelagos form continents of structure, all set in a sea of unimaginable peaceful nothing. It is a hierarchy of quiet belonging, from our living room on Earth all the way out to the cosmic web. It is all above us, in every direction we look. But now, let us turn our gentle curiosity to the other part of the question. What could possibly lie below our solar system? This is a trickier thought, because in space there is no true up or down. But if we think of below not as a direction toward our feet, but as a direction inward toward smaller and smaller scales, a whole new universe of wonder opens up. It is a universe not of vast emptiness, but of incredible complexity and ceaseless activity. It is the universe within. So let us journey downward from the familiar scale of our solar system. We begin with our own world, the Earth. Below the system is the planet itself, with its mountains and oceans, its forests and cities. And below that, the intricate web of life. Every leaf, every insect, every breath you take is part of the solar system, existing below the grand orbital mechanics. Your very body, made of stardust, is a part of this cosmic neighborhood. You are a citizen of the solar system, living on its third planet. That is the most intimate answer to what is below. It is us. It is all the life, the geology, the weather, the art, and love and quiet moments that happen in the shelter of our sun's light. But we can go further down. Let us shrink our perspective, down past the scale of cities, of trees, of humans, down to the world of the very small. Below the level of our eyesight, there is a bustling universe, the world of cells, of bacteria, of viruses. A single drop of water from our planet contains a miniature ecosystem, teeming with life forms that have their own rhythms and cycles. They live and die on a grain of sand, utterly unaware of the planets orbiting overhead. This biosphere, this thin, vibrant film on our planet's surface, is a fundamental part of what exists below the solar system. It is the part that is alive, the part that turns starlight into consciousness, and we go smaller still, to the molecular level, the air we breathe, the water we drink, the DNA that codes for life. All of it is a dance of molecules, atoms linking and unlinking in an endless, silent chemical ballet. And these atoms, every single one of them, have a story that leads directly back to the stars above. The carbon in your bones, the oxygen in your lungs, the iron in your blood, were all forged in the hearts of ancient stars that lived and died long before our sun was born. So, the below is not separate from the above. It is the same stuff, arranged in an infinitely delicate and precious way. The universe expressed in a living, breathing form. Deeper we go, to the atomic scale, a realm of incredible emptiness and frantic energy. A single atom is mostly empty space. If the nucleus of a hydrogen atom were the size of a marble, the electron whirling around it would be over a mile away. Almost all the solid matter we feel is, at its heart, empty space, held together by invisible forces. This is a profound thought. The ground beneath your feet, the chair you sit on, your own hand, all are vast, open lattices of tiny points of energy humming in the void. We are, all of us, made of space and light and force. And what lies below the atom? The subatomic particles, the protons and neutrons that form the nucleus, and the electrons that dance in their clouds. And within the protons and neutrons, we find the quarks, held together by gluons. This is the frontier of our understanding, the quantum realm. Here, the rules are strange and beautiful. Particles are also waves. Things can be in two places at once until we look at them. Empty space is not empty at all, but a seething, bubbling foam of potential where particles flicker in and out of existence. This quantum vacuum is the very foundation of all reality. It is the canvas upon which the universe is painted. So, below our solar system, below our planet, below our bodies, down at the very bedrock of existence, there is this humming, vibrant field of potential. The solar system, with all its planets and moons, is a pattern, a fluctuation, in this fundamental energy field. It is a gentle ripple on a deep, quiet, and unimaginably powerful sea. So we have two journeys, one outward, into ever greater scales of space and majesty, and one inward, into ever smaller scales of complexity and mystery. And they meet in a beautiful circular thought. The vast cosmic web of galaxies and the frothing quantum foam are not opposites. They are two expressions of the same single universe. The forces that hold a galaxy together, gravity, are the same forces that were set in motion at the very beginning. The quantum rules that govern a single electron are the rules that allowed atoms to form, then stars, then planets, then us. Our solar system is the meeting point of these two infinities. It is the middle ground. It is not insignificant because it sits between the immensely large and the incredibly small. It is, in fact, the precious bridge between them. It is the place where the universe, through billions of years of patient work, arranged stardust into a form that could look back out at the stars and wonder about them. We are the universe becoming aware of itself, and we exist right here, in this solar system, on this planet. As we float here in our minds between the infinite above and the infinite below, a deep sense of peace might settle over you. There is no need to feel small. Instead, feel connected. You are literally made from the debris of exploded stars. The calcium in your teeth, the potassium in your nerves, the phosphorus in your bones, all were cooked in stellar furnaces. You are a way for the cosmos to know itself, and you exist in a location that is both spectacularly ordinary and miraculously rare. An ordinary star in an ordinary galaxy, but on a planet that is just the right distance, with just the right chemistry, to spark and sustain the flame of awareness. Think of the night sky again. Every point of light you see is a sun, and many of those suns likely have planets of their own. Some of those planets may have their own oceans, their own mountains, their own quiet nights. And on some, perhaps, other beings are looking up at their sky, seeing our sun as just another faint star, and asking the same questions, wondering what lies above and below their own celestial home. This thought does not isolate us. It connects us across the light years. We are all, everywhere in the universe, children of the stars, living on islands in the great dark, pondering the mystery of our existence. So, as this journey of the mind comes to a gentle close, let us return to that feeling of floating, the gentle darkness, the silent, steady points of light. There is no rush. There is no endpoint to reach. The wonder is not in a destination, but in the journey itself, and in the quiet realization it brings. Above us, an expanse of majestic, peaceful architecture built from gravity and time. Below us, a world of intricate humming complexity built from quantum whispers and stellar legacy. And here we are, suspended perfectly between them, in the gentle light of our sun. You are not just in the universe is in you. And in this quiet moment, that truth can be a deep and soothing comfort. There is no separation. You belong to this cosmos, from the smallest quark in your cells to the most distant galaxy spinning in the void. It is all one, vast, interconnected whole. And for tonight, that is enough. That is more than enough. So let the sense of scale dissolve. Let the questions soften into simple awe. And just be here, a conscious part of it all, breathing slowly under the same ancient stars that guided our ancestors and will guide generations to come. The universe is above you, below you, and within you, and it is in this moment perfectly still, perfectly peaceful, and full of a quiet, endless wonder. Rest now in that knowing, and as you rest in that knowing, let your imagination linger on that bridge, that middle ground which is our home. Think of the solar system not as a collection of separate objects, but as a single, flowing entity. The sun's light and wind flow outward, touching every planet, every comet, every speck of dust, in a vast spherical bubble called the heliosphere. This is our star's true domain, its gentle influence creating a protective cocoon against the true interstellar medium. We live inside the sun's atmosphere in a sense. Every time you feel sunlight on your skin, you are feeling the outermost, most tender reach of a stellar giant, a touch that has traveled for 8 minutes across the void to warm you. That connection is immediate and physical. It is a daily reminder that we are not merely observers of this system, but participants, bathed in its constant, life-giving stream. Consider the paths traced through this space, the orbits that have continued with such faithfulness for billions of years. They are not just lines on a chart. They are a slow, celestial harmony. Jupiter, with its great gravity, shepherds asteroids and shapes the architecture of the inner system. Saturn's rings, composed of countless ice particles, each following its own perfect orbit, create a spectacle of silent, clockwork beauty. The solar system is in motion, but it is a motion of profound peace, of balance so delicate and yet so resilient that it has cradled life for eons. This is the rhythm that exists below the galaxy's grand spin, a softer, closer rhythm, the rhythm of a year, of a season, of a moon cycle. These are the pulses of our immediate cosmic home, rhythms written into the biology of every living thing on Earth. Your own body responds to these cycles in ways subtle and deep. You are tuned to the music of this middle realm. Now, let your mind drift back to that concept of below, to the quantum world, and see if you can feel the connection to this celestial scale. It is a connection not of size, but of pattern, of relationship. The atom, with its nucleus and orbiting electrons, is so often compared to a miniature solar system. While the physics are profoundly different, the echo of that pattern is a soothing one. It suggests a universe that finds certain forms beautiful, certain arrangements stable, from the unimaginably small to the breathtakingly large. It is a hint of a deeper unity. The force that holds the electron in a loose embrace around its nucleus is electromagnetism, and that same force, in a different guise, is the force that makes the sunlight warm, that drives the chemistry of life, that allows your nerves to carry thoughts. The threads weave through every layer of reality, binding them. Think of the very act of perception that allows this journey. The light from a distant star, traveling for centuries, finally enters the eye of a being on a small, rocky world. That light, a packet of energy, a quantum phenomenon, strikes a molecule in a retinal cell, causing a change that becomes an electrical signal, which becomes a pattern in the brain, which becomes an image, a feeling, a thought of wonder. The entire universe, from the quantum to the galactic, is involved in that single moment of awe. The above and the below collaborate to create the experience of being here now, conscious. You are the locus where these vast scales meet and are translated into meaning. There is no more intimate point in the cosmos. Perhaps now, we can contemplate the spaces in between these scales, not just the vast interstellar voids, but the quieter spaces closer to home, the space between planets, which we often think of as empty. But it is not empty. It is filled with the solar wind, a breeze of particles streaming from the sun. It is threaded by magnetic fields, invisible lines of force that guide and protect. It is dusted with microscopic grains, the leftover stuff of planetary formation, drifting like snow in slow motion, and occasionally, graced by the passage of a comet, a visitor from the system's outer reaches, leaving a temporary glowing trail as it is warmed by the sun. This interplanetary space is an environment, subtle and gentle, through which the worlds move like great ships on a calm, invisible sea. And what of the spaces within our own world, the deep ocean trenches where sunlight never reaches, and yet life thrives by chemosynthesis, drawing energy from the Earth's own hot interior? The vast subterranean networks of rock and aquifer, where water moves slowly through the dark over centuries. These are inner spaces that feel as alien and remote as any planet, yet they are integral parts of the below that supports the vibrant surface. They remind us that complexity and resilience exist in the dark and the quiet, not just in the light. Our planet has its own hidden depths, echoing the cosmic ones. As we float with these thoughts, we might also consider time as a dimension of this journey. What exists above and below can also be thought of as what came before and what will come after. Below, in the past, is the protoplanetary disk, the swirling cloud of gas and dust that coalesced into our sun and its planets. It is the long, slow cooling of the Earth, the first tentative molecules of life in a warm little pond. It is the age of dinosaurs, the rise of mammals, the dawn of human consciousness looking up at the same stars. Above, in the future, is the continued slow drift of the stars, the eventual merging of our Milky Way with the Andromeda Galaxy in a slow-motion dance that will reshape the night sky over billions of years. It is the sun, growing older, warmer, eventually becoming a red giant and then a quiet white dwarf. The solar, imagine for a moment that you are looking up at the night sky. You find that bright, steady point of light, not a star, but a planet. Jupiter. It has been a constant presence for all of human history, a wandering star to the ancients, a swirling marble of cloud to the first astronomers who pointed their telescopes its way. It feels permanent. It feels known. But out there, in the deep quiet of space, something is happening. Something subtle and strange and slowly unfolding. Jupiter is not quite behaving as we thought it would. It holds secrets beneath its famous bands, mysteries in its endless storms, and recent whispers from science suggest we are only just beginning to understand the true nature of this giant world. So let us drift toward it tonight, not with urgency, but with a soft and wondering curiosity. Let us explore what it might mean when we say that something weird is happening to Jupiter. To understand the strange, we must first appreciate the familiar. Jupiter is a world of magnificent scale. It is so large that all the other planets in our solar system could fit inside it with room to spare. It is not a solid world of rock and soil like our own, but a gas giant, a vast sphere of mostly hydrogen and helium with no surface to speak of, only layers of atmosphere growing denser and hotter until they blend into a strange metallic fluid deep within. Its most famous feature is the Great Red Spot, a storm wider than our entire planet that has raged for centuries, perhaps longer. From afar, through telescopes and the lenses of spacecraft, Jupiter presents a face of serene and beautiful turmoil. Swirling bands of cream, ochre, and tan stripe its face, flowing in opposite directions, driven by jet streams that race at hundreds of miles per hour. It is a dynamic world, a churning cauldron of weather, and for a long time we thought we understood its rhythms. We thought its immense distance from the sun, its own internal heat radiating from a slowly shrinking core, and its rapid rotation created a system that was, in its own violent way, predictable. But the closer we look, and the longer we watch, the more we see patterns that puzzle us. The giant is whispering, and we are slowly learning to listen. One of the most profound mysteries of Jupiter has always been what lies beneath those magnificent clouds. The cloud tops we see are just the outermost layer of an atmosphere thousands of miles deep. They are so thick, so dense, and so turbulent that they have acted as a perfect veil. No probe has ever penetrated far enough to tell us what is below. The Galileo spacecraft, when it ended its mission, was sent plunging into Jupiter's atmosphere, and it transmitted data for only about an hour before the immense pressure and heat crushed and vaporized it. It was like throwing a stone into an ocean and trying to understand the seafloor from the briefest splash. So, for centuries, we have been astronomers peering at the surface of a deep, deep sea, trying to guess the creatures and landscapes that dwell in its abyss. What is the true composition of Jupiter? How much water is hidden down there? How much oxygen? These are not just questions about one planet. They are clues to the very beginning of our entire solar system. Jupiter was likely the first planet to form, and its composition is a frozen recipe from the primordial cloud of gas and dust that gave birth to our Sun and all the worlds that orbit it. To understand what Jupiter is made of is to understand our own origins. Recently, scientists have taken a new approach to this ancient puzzle. Instead of just observing the cloud tops, they have begun to build incredibly detailed digital simulations, combining the physics of fluid motion with the complex chemistry of thousands of reactions. It is like creating a Jupiter in a supercomputer, a virtual world where they can experiment and observe processes that are impossible to see directly. And this new model has revealed something quite significant. It suggests that Jupiter likely holds much more oxygen than we previously suspected. In fact, the estimate is that Jupiter contains about 1.5 times more oxygen than our Sun. This is a key piece of the puzzle. If Jupiter, the solar system's firstborn, has that much oxygen, it changes the story of how the building blocks of planets were distributed in that early cosmic cloud. It hints that the region where Jupiter formed was richer in certain icy materials than we thought. This oxygen is not in the form of the air we breathe, of course. Deep within Jupiter, under crushing pressures, it is bound with hydrogen to form water or mixed into other exotic compounds. This finding helps resolve a long-standing debate and sharpens the picture of our solar system's infancy. But it also highlights a deeper truth. The gases in Jupiter's immense atmosphere move and mix much more slowly than scientists once believed. The churning we see on the surface is just the very top of a profoundly sluggish, deep ocean of gas. Processes that might take years or decades in Earth's atmosphere could take centuries or millennia within Jupiter. It is a world operating on a timescale almost incomprehensible to us, a giant breathing with an unimaginably slow breath. This leads us to the other, more immediate strangeness. While the deep interior may be slow, the upper atmosphere where the clouds live is showing us patterns that defy our expectations in a different way. For 40 years now, we have been studying Jupiter's weather, not just with occasional spacecraft flybys, but with persistent observation from telescopes on Earth and in space. We have compiled a record, a 4-decade-long diary of Jupiter's temperatures and cloud movements. And this long view has revealed something odd. Jupiter experiences what look like hot and cold periods. Its upper atmosphere, in specific bands and at specific latitudes, seems to warm and cool in cycles. On Earth, such cycles are the heartbeat of our seasons, caused by the tilt of our axis as we orbit the Sun. But Jupiter's axis is only tilted by about 3 degrees. It spins almost perfectly upright. It does not have seasons in the way we understand them. There is no planetary reason for its equator to be significantly warmer or cooler than its poles in a cyclical pattern. And yet, the data shows these oscillations happening. It is as if the planet has its own internal rhythmic pulse of heat that has nothing to do with the distant Sun. The changes are not dramatic, not like a switch being flipped, but they are consistent and strange. They suggest that the engine of Jupiter's weather, the transfer of heat from its hot interior out into space, is far more complex and poorly understood than our textbooks suggested. The giant planet seems to be marching to the beat of its own, very slow and very mysterious drum. Think about what this means. Here is a world, the largest in our neighborhood, a fundamental anchor point in our solar system. We have mapped its storms, counted its moons, and sent robotic emissaries to orbit it. And yet, it is telling us that the basic forces that drive its climate are not what we modeled them to be. The planet is not acting quite like a planet should, according to our simpler models. It has its own logic, its own pace, its own hidden mechanisms that we are only beginning to sense. This is the quiet wonder of discovery. It is not about finding answers that fit neatly into boxes. It is about realizing the questions were not even big enough to begin with. Jupiter is reminding us of the humility of science. Every answer unveils a deeper, more intricate question. Consider the great red spot itself. We have watched it shrink and change color over the decades. We have seen smaller storms get swallowed by it, or sometimes crash against its swirling walls and break apart. It is a permanent yet changing feature, an island of fury in a fluid sky. But what fuels it? What keeps a storm alive for hundreds of years? The new understanding of slow atmospheric mixing and internal heat pulses might hold clues. Perhaps the spot is not just a surface weather pattern, but a chimney, a conduit for energy and material from the deep interior, which gives it a longevity no storm on Earth could ever hope to have. Its redness, likely caused by complex chemicals being dredged up from below and cooked by ultraviolet light, is a direct window into processes happening dozens of miles underneath the cloud tops we can see. It is a symbol of the hidden Jupiter, the world beneath the veil. And then there are the colors of Jupiter's bands, those beautiful tawny browns, tans, and whites. They are created by different chemical compounds, ammonia, ammonium hydrosulfide, and traces of water, existing at different altitudes and temperatures. The lighter bands are zones where gas is rising. The darker bands are belts where gas is sinking. This simple up and down motion, driven by Jupiter's fierce rotation, creates the striped pattern. But the new research suggests the chemistry governing these colors is immensely complex. Molecules are not just passively riding the winds. They are condensing into droplets, evaporating back into gas, and undergoing countless chemical reactions as they are transported from the hot, high-pressure depths to the cold, thin upper layers. The beautiful face of Jupiter is a constantly changing chemical painting, its palette determined by processes we are only now learning to simulate. What looks like a simple band of color is the end result of a planetary-scale alchemy, a slow distillation happening over epochs. So, when we say something weird is happening on Jupiter, we are not talking about a sudden, alarming change. We are not describing a cataclysm or an imminent transformation. The weirdness is in the subtlety. It is in the slow realization that this familiar giant, this king of planets, operates on principles more nuanced and mysterious than we gave it credit for. Its atmosphere mixes slowly. Its heat pulses in unexplained rhythms. Its composition tells a story of the solar system's birth that we are still deciphering. This is the calm, ongoing weirdness of a universe that is always more intricate than it appears. Jupiter is not breaking the rules. It is showing us that the rule book we wrote was only a first draft, a simplified sketch of a masterpiece. As you lie there, thinking about that distant point of light, you can picture it not as a static picture in a textbook, but as living, breathing entity, a world of unimaginable depth, where storms last for centuries and the air itself moves with the patience of geology, a world where the temperature fluctuates to a rhythm we cannot yet hear, driven by an inner fire and a logic all its own. The sense of wonder comes not from fear of the strange, but from a gentle appreciation of the vast unknown that resides even in our own celestial backyard. Jupiter has been there all along, holding its secrets close, revealing them slowly, one whispered datum at a time, across decades of patient observation. There is a profound peace in this realization. The universe is not a solved puzzle. It is a story that is still being told, and we are here, quiet and small, listening to one chapter of it. The weirdness on Jupiter is a gift. It is a reminder that curiosity is a gentle, endless journey. There will always be another layer to peel back, another question to ask, another mystery waiting in the soft glow of a distant world. So the next time you see Jupiter shining in the night sky, you can know that you are looking at more than a planet. You are looking at a question mark wrapped in clouds, a giant enigma spinning silently in the void, doing things we are just beginning to understand. And there is a deep, quiet comfort in that. The cosmos is alive with slow, majestic change, and our role is simply to watch, to learn, and to wonder. So, let your mind drift with that thought, as softly as a cloud drifting in Jupiter's upper atmosphere. There is no need for conclusions, only contemplation. The giant is there, as it always has been, doing something weird and wonderful, a testament to the infinite complexity of the universe we call home. And that is a thought peaceful enough to drift away on, into quiet and dreamless sleep, under the same sky that holds such gentle, endless mystery. And as we contemplate this slow-motion giant, we can begin to imagine the sensory experience of being there, not as a solid being, for there is no ground to stand on, but as a consciousness drifting through those layers. Imagine descending from the blackness of space, approaching those creamy, swirling cloud tops. The first thing you might sense is the silence, a profound and absolute quiet, for sound needs a medium to travel. And here, the medium is so thin and vast that a storm the size of a continent would make no audible roar to an outside observer. But within, if you could listen, the sound would be a deep basso profundo rumble, vibrations felt more than heard, the groan of a world under its own immense weight. You would pass through the high, wispy ammonia cirrus clouds, crystals sparkling in the faint sunlight that is only 1/25th as bright as it is on Earth. The light here is a perpetual soft twilight, tinged with gold and brown. As you drift deeper, the pressure builds, a gentle but insistent embrace that would quickly become crushing. The clouds thicken into bands, great rivers of atmosphere flowing in opposite directions. Here, in the zones and belts, you would be caught in jet streams moving at over 300 miles per hour, yet the scale is so grand that the motion might feel stately, inexorable, like being in the heart of a planetary tide. The colors here are not the vivid hues of enhanced spacecraft images, but more muted, subtle shades of cream, rust, and pale gray, with occasional flashes of deeper ochre where compounds well up from the abyss below. Deeper still, the sunlight fades completely. You are in the eternal night of Jupiter's middle atmosphere. Here, if there were eyes to see, they might perceive the ghostly glow of heat lightning, vast discharges of energy illuminating banks of clouds made not of water, but of ammonium hydrosulfide, giving off a faint sulphurous scent, if such a thing could be smelled. The temperature, curiously, might be quite comfortable here, even room temperature in certain layers, before plunging again and then beginning its final fierce climb into the inferno. This is a realm of perpetual chemical industry. Molecules split and recombine, forming intricate chains, condensing into droplets and vaporizing again, all in a slow, three-dimensional dance dictated by the slow circulation of the deep atmosphere. The new models tell us this dance is far more leisurely than we ever imagined. A parcel of gas, carrying its unique signature of chemicals, might take centuries to complete a single loop from the deep interior to the cloud tops and back again. This is the sluggish heartbeat of Jupiter. And what of that deep interior? As we sink further, pressure turns the gaseous hydrogen into a fluid, and then, thousands of miles down, into a strange metallic liquid. This is not a place of familiar matter. It is an ocean of liquid hydrogen, electrically conductive, swirling around a core that is still a mystery. Perhaps a dense ball of rock and ice, perhaps a diffuse, diluted mixture of elements slowly dissolving into the surrounding metallic sea. The heat here is tremendous, left over from the planet's violent birth, and perhaps from the slow, gravitational squeezing of its own mass. This internal furnace is the ultimate engine for everything above. It is this heat, seeping outward with incredible slowness, that drives the convection, fuels the storms, and creates those mysterious thermal pulses in the upper atmosphere that we detect as warm and cool periods. The planet is radiating more than twice the energy it receives from the sun. It has its own source of warmth, its own inner fire, and the rhythm of that fire's release into the atmosphere is what we are only beginning to perceive as a weird, arrhythmic pulse. This brings us back to the question of why. Why do these thermal cycles exist without seasons? One contemplative possibility lies in the very slowness of the system. Jupiter is not just a ball of gas. It is a fluid planet through and through. The movements within its metallic hydrogen interior, the dynamo that generates its powerful magnetic field, the strongest in the solar system. These processes might have their own long-term cycles. Waves of energy, perhaps akin to the ocean oscillations on Earth, but on a planetary and century-long scale, could slowly propagate upward. They might be influenced by the complex gravitational tugs of Jupiter's many moons, especially the large Galilean ones. Io, Europa, Ganymede, and Callisto constantly stretch and squeeze Jupiter's interior through tidal forces, minutely affecting its fluid dynamics. Over decades, these subtle nudges could manifest as variations in how heat is distributed in the upper layers. It is a symphony of forces: internal heat, deep circulation, magnetic dynamics, and external tides, playing a piece so long that a human lifetime can only hear a few notes. What we call weird is simply our first faint hearing of this symphony. Consider the clouds themselves as characters in this slow drama. The white ammonia clouds are the highest, the cold ones. Below them, in a layer with more pressure and slightly warmer conditions, exist the ammonium hydrosulfide clouds, which give Jupiter its tawny browns and tans. Deeper still, where the pressure is dozens of times that of Earth's surface and the temperature climbs, there should be clouds of water vapor. This water layer is one of the great hidden realms. The new findings about abundant oxygen directly point to a wealth of water hidden in these depths, but accessing it, even with our most advanced simulations, is a challenge. This water cloud layer may be where some of the most significant weather occurs, a realm of droplets and storms entirely hidden from our view, yet its effects ripple upward to shape the patterns we see. A slow upwelling from this hidden ocean of vapor could, over many years, alter the chemistry and temperature of the upper cloud decks, contributing to the cyclical patterns we observe. There is also the fascinating interplay of chemistry and motion. On Earth, our weather is largely a physical phenomenon: temperature, pressure, wind. Chemistry plays a secondary role. On Jupiter, they are intimately, fundamentally linked. The colors are chemistry. The storm longevity is chemistry. The very structure of the cloud layers is a chemical stratification. As gases rise from the hot depths, they cool. Different compounds condense out at specific temperatures and pressures, forming clouds at precise altitudes. But the new combined models show this is not a one-way street. These cloud droplets do not just sit there. They fall, they evaporate, they release latent heat, which in turn drives more circulation. They act as tracers, showing the pathways of the deep winds, and they shield the lower atmosphere from our view, creating the veil that has made Jupiter's composition so hard to pin down. The weirdness, then, is partly in realizing that Jupiter's atmosphere is not just a fluid system, but a chemical reactor of unimaginable scale. Its beauty is a direct visual output of its constant, slow, alchemical transformation. As we watch from our distant vantage point, with instruments growing ever more sensitive, we are essentially learning to read this giant's vital signs. The infrared glows that reveal temperature, the subtle changes in cloud color and reflectivity, the slight shifts in wind speed measured by tracking cloud features over decades. These are Jupiter's pulse, its respiration, its slow blink. And the diagnosis so far is that it is a far more complex and interesting patient than we assumed. It defies simple categorization. It is not merely a failed star, nor is it simply a larger version of the other gas giants. It is its own unique class of world, the archetype of a gas giant, and it is teaching us that the archetype itself is richer and stranger than the definition we wrote for it. This has profound implications beyond Jupiter itself. We have now discovered thousands of planets orbiting other stars. A great many of them are gas giants, some larger than Jupiter, some orbiting perilously close to their suns. We call them hot Jupiters. For a long time, we used our solar system's Jupiter as the model for understanding all such worlds. But if our own Jupiter is more mysterious than we thought, how much more mysterious must those distant cousins be? Our Jupiter, with its complex, slow-moving atmosphere and internal heat cycles, provides a benchmark, but a benchmark that is now shimmering with complexity. It tells us that to understand exoplanets, we must first humble ourselves before the deep, slow mysteries of the one that resides in our own cosmic neighborhood. Every strange datum from Jupiter is a cautionary note, a reminder that the universe rarely simplifies itself for our convenience. So, as you let your mind wander across the gulf of space to that waferly banded sphere, try to feel the scale of time as well as space. Imagine a storm that began before the invention of the telescope, that has persisted through the entire modern age of humanity, and that shows only gradual, gentle change. Imagine you are floating in the deepest, darkest ocean of space. The silence is absolute, a profound quiet that stretches across light years. Around you, stars are not just points of light, but distant suns, each one a silent sentinel to its own private collection of worlds. Most of those worlds are nothing like our own. They are not places of gentle breezes and liquid water. They are monuments to cosmic violence, to physics pushed to its most extreme and unforgiving limits. They are places where the very concepts of day and night, of solid ground and open sky, are twisted into forms of quiet, eternal horror. Tonight, we will drift past a few of them. We will visit some of the most unsettling, the most hostile, the most deeply alien planets ever discovered by human science. This is not a journey of adventure, but of contemplation, a slow, dark look into the abyss and at the strange, terrible beauty that stares back. Our first destination is a world of fire and stone, a place where the sky itself is a crushing, incandescent furnace. Its name is Corot 7b. From a distance, it might seem familiar, a rocky world not so different in size from our own Earth. But that familiarity is a cruel illusion. Corot 7b is locked in a deadly embrace with its star. One side of the planet perpetually faces the searing light, while the other is turned forever to the frozen dark. On the day side, the temperature does not merely rise, it soars to heights that defy comprehension. The surface glows with a heat exceeding 2,600 degrees Celsius. At such temperatures, rock does not simply sit there. It melts, it vaporizes. The very ground beneath your feet would turn into a swirling, superheated silicate mist. Now, imagine the weather on such a world. The vaporized rock, these minerals turn to gas, rise into the slightly cooler upper layers of the atmosphere. There, they do something both mundane and utterly terrifying. They condense. Just as water vapor in our sky forms clouds and then rain, on Corot 7b, The silicon and magnesium and iron vapors coalesce. They form clouds of tiny mineral droplets, and then they fall. The sky on the day side of Corot 7b rains pebbles and gravel and stones, a slow, relentless hail of rock, born from the vaporized crust, falling back into the global ocean of lava below. It is a world caught in a perpetual violent cycle of creation and destruction, where the landscape is both liquid and solid, where the atmosphere is made of stone. The night side offers no refuge, only a deep absolute cold nearing 230 degrees below zero, a silent, airless desert locked in permanent shadow. This is not a planet. It is a geological clockwork of pure, elemental fury. We move on, leaving the furnace world behind, drifting further into the void. Our next encounter is not with a planet of fire, but with a world of profound, majestic, and deeply unsettling scale. We approach a gas giant known as J1407b. At first, it seems reminiscent of our own Saturn, a majestic sphere adorned with rings of ice and dust. But as we draw nearer, the sense of scale begins to warp. These are not the delicate, glittering bands we know. The rings of J1407b are a system of cosmic proportions so vast they strain the imagination. They stretch out into space for over 110 million miles. To put that into perspective, that distance is greater than the span between our Earth and our Sun. If Saturn's rings were a bracelet, the rings of J1407b would be a celestial highway encircling a world. This immense structure speaks of a violent and chaotic past. Rings of such scale are not born from gentle processes. They are the graves of moons. The gravitational pull of J1407b, a behemoth potentially dozens of times more massive than Jupiter, is thought to have been so powerful that it reached out and shredded any large satellites that dared to orbit too close. What we see now is the beautiful glittering debris field of that destruction, a monument to celestial violence frozen in silent, graceful orbits. Within these vast rings, there are gaps, dark lanes where the material has been cleared. Some of these gaps may themselves be the signatures of smaller, unborn worlds trying to form, or of past collisions so massive they carved canyons through the ice. To drift through this ring system would be to sail through a field of frozen wreckage on a scale that dwarfs entire solar systems, a constant, silent reminder of the crushing power of gravity. Let us shift our gaze now to a world that defies one of our most basic understandings of nature. A planet where logic seems inverted, where fire and ice exist not as opposites, but in a horrifying union. Its name is Gliese 436b. This is a world roughly the size of Neptune, and it orbits so close to its dim red star that its year is just a few Earth days long. The radiation it receives bathes its surface in a heat of nearly 500 degrees Celsius. On any world we know, such heat would mean scorched rock, boiling oceans, an atmosphere of searing vapor. But Gliese 436b is different. Despite the blistering heat, astronomers believe this world is covered in ice. Not the fragile crystalline ice of Earth, but something far stranger and more formidable. This is a substance called Ice X, or perhaps other exotic high-pressure forms of water ice. The secret is not temperature, but pressure. The gravitational force on Gliese 436b is immense, so powerful that it compresses matter into states we can barely conceive. The water vapor in its atmosphere is crushed, forced into a solid state even under the intense stellar heat. The surface, then, might be a landscape of burning ice. Ice that does not melt, ice that is hotter than a blazing furnace. If you could stand on it, the very ground would be a solid, searing slab, a paradox made manifest. Furthermore, the star's radiation is slowly stripping away the planet's hydrogen atmosphere, blowing it out into space to form a vast, ghostly tail millions of miles long, like a comet sentenced to eternally circle its own doom. It is a world trapped by its own immense weight, wearing a coat of frozen flame. From the paradox of burning ice, we journey to a world of breathtaking beauty and lethal grace, a sapphire blue marble hanging in the blackness. Do not be fooled by its appearance. This is HD 199733b, and it is perhaps one of the most viciously inhospitable places ever discovered. That deep, captivating azure hue does not come from tranquil oceans, but from a hazy, scorched atmosphere rich in silicate particles. This is a world of endless, violent storm. The temperature here is a constant 1700 degrees Fahrenheit. The atmosphere is not still. It is a screaming maelstrom. Winds race across the planet at speeds that eclipse 5,000 miles per hour. These are not winds as we understand them. They are supersonic tsunamis of superheated gas, moving at 7 times the speed of sound. Within this raging, incandescent atmosphere, those silicate particles are not mere dust. They are the seeds of a terrible precipitation. The heat melts the silicates into droplets of molten glass, and the hurricane-force winds whip these droplets horizontally, sending them slicing through the atmosphere at bullet speeds. It rains sideways on HD 1189733b, a perpetual blistering storm of molten glass shards, scouring the landscape in a deafening, fiery haze. The beautiful blue world is, in truth, a planetary-scale sandblaster, a sphere of endless, abrasive fury, where the very air is a lethal, cutting fluid. We must venture further into realms where planets are not born in the gentle disk around young stars, but forged in the cataclysmic deaths of their suns. These are the so-called zombie worlds, planets that orbit the corpses of stars. Consider a system like PSR B57+12. Here, the central star is no longer a fusion-powered sun. It is a pulsar, the ultra-dense, rapidly spinning remnant of a supernova explosion. This city-sized object contains the mass of our entire sun, spinning hundreds of times per second, emitting beams of deadly radiation that sweep through space like a cosmic lighthouse from hell. And yet, around this stellar corpse, planets have been found. They are worlds that somehow survived the apocalyptic violence of the supernova that created their pulsar master. Or perhaps they formed from the fallback debris of that very explosion. To exist here is to live under a dying sun. The sky would be black, pierced only by the rhythmic, piercing flash of the pulsar's beams, beams of X-rays and gamma rays that would sterilize the surface in an instant. Any atmosphere would have been blasted away eons ago. These planets are likely barren, airless chunks of rock or diamond, bathed in lethal radiation, tidally locked and scorched on one side by the pulsar's energy, frozen on the other. They are monuments to survival in a universe that has already ended, orbiting a ghost. Our journey takes us to even more isolated and desolate realms. Imagine a planet not bound to any star at all, a rogue planet, flung from its native solar system by gravitational chaos, now drifting alone through the interstellar void. These are dark wanderers, and one of the most fascinating candidates is known as CFBDSIR 2149-0403. On such a world, there is no sunrise, no sunset. The sky is a permanent, unbroken tapestry of black, dotted with the faint, unmoving pinpricks of distant galaxies. The only source of heat is the feeble remnant warmth from its own formation, and the slow radioactive decay in its core. The surface would be a landscape of profound cold, approaching absolute zero. Any atmosphere would likely have frozen out, falling as snow of nitrogen, oxygen, or methane, creating a bizarre, frozen wasteland. Yet, in the crushing pressure of a thick hydrogen atmosphere, some of these rogue gas giants might retain a lukewarm interior. But the surface, the boundary with space, is a realm of eternal midnight and deep freeze. The loneliness is absolute. To stand on such a world is to experience the ultimate isolation, a tiny point of matter adrift in an ocean of nothingness, with no star to call home, forever traveling the empty highways between suns. Let us contemplate a world of pressure, so extreme, it transforms the very essence of matter. We arrive at a super-Earth, a planet like 55 Cancri E, a world possibly rich in carbon. Under the immense gravitational force of a world several times more massive than Earth, carbon can be subjected to conditions so severe that chemistry itself bends. The heat is tremendous, thousands of degrees. The pressure, millions of times greater than what we feel at sea level. In such a forge, carbon crystallizes not into graphite, but into its most lustrous and yielding form, diamond. It is theorized that planets like this could have vast strata of diamond within them, not mere veins or deposits, but entire layers, continents worth of crystalline carbon. The core might be a solid mass of diamond. The mantle could be a strange high-pressure fluid or solid carbon mix. The surface, if any solid surface exists under a thick, hot atmosphere, might be littered with diamond mountains glittering under a dim red sun. It is a world of obscene, static wealth, a treasure locked in a vault of impossible pressure and heat, forever out of reach, a beautiful and sterile monument to cosmic alchemy. We turn next to a world that presents a different kind of horror, not of heat or storm, but of a profound and eerie resemblance gone wrong. Kepler 438e was once hailed as one of the most Earth-like exoplanets known, orbiting comfortably within the habitable zone of its star. But its star, a red dwarf, is prone to fits of unimaginable violence. Red dwarfs can unleash superflares, stellar eruptions that dwarf anything our sun has ever produced. Kepler 438b is bombarded by these superflares with terrifying regularity. Each flare unleashes a torrent of X-ray and ultraviolet radiation powerful enough to strip away not just an atmosphere, but potentially scour the very rock of the surface. Any emerging biosphere would be sterilized again and again. The planet might be Earth-sized. It might have the right temperature for liquid water, but its sky is periodically lit by the flash of a stellar apocalypse, bathing the world in lethal radiation. It is a cruel joke of cosmic real estate, a promising world perpetually poisoned by its own sun, a lesson that habitability requires not just the right place, but also a quiet, stable star. Now, let us venture to the edge of a black hole. While not a planet in the traditional sense, the concept of a world orbiting such an object stretches the imagination to its breaking point. Imagine a planet, or the remnants of one, in a tight orbit around a stellar mass black hole. The sky would be a twisted panorama. Gravitational lensing would warp the light from the background stars into strange, shifting rings and arcs. There would be no primary light source, only this distorted starlight and the utter blackness of the accretion disk, if one exists, a silent whirlpool of doomed matter. The tidal forces would be immense, stretching and compressing the world itself. Time would slow down relative to the rest of the universe. The planet would be locked in a dance with pure gravity, with the point of no return just a momentary misstep away. It would be a world living on borrowed time, in a cemetery of space-time, where the laws of physics as we know them begin to unravel at the horizon. The silence here would be deeper than anywhere else, a silence punctuated only by the imaginary roar of infalling matter and the relentless pull of the infinite dark. Finally, we come to a world that embodies a slow, global extinction event. Venus, our sister planet, is a stark and sobering reminder that hell can exist right next door. While not an exoplanet, it serves as the ultimate prototype for a horrifying planet. A runaway greenhouse effect has transformed Venus into a pressure cooker. The surface temperature is hot enough to melt lead, around 460 degrees Celsius. The atmospheric pressure is 92 times that of Earth's, equivalent to the pressure found a kilometer deep in our oceans. The sky is a perpetual thick blanket of yellow sulfuric acid clouds, and it rains acid, though the droplets evaporate long before they reach the inferno below. The surface is a volcanic plain, crushed under the weight of its own toxic sky. Venus shows us that a planet can take a wrong turn, that conditions can spiral into a permanent global catastrophe. It is a tomb world, a warning written in acid and fire, proving that a planet with similar beginnings to Earth can become a place of utter, relentless hostility. As our journey ends, we are left floating once more in the quiet dark. The horrifying planets we have visited are not monsters. They are simply nature, expressed in its most raw and extreme forms. They are demonstrations of the infinite variety of physical laws, of what happens when heat, pressure, gravity, and chemistry are dialed to values beyond our earthly experience. Their horror is, in a way, a human projection. They are hostile to us, to our fragile, water-based, temperature-sensitive form of life. But in their own right, they are perfect. They are equilibrium states of matter and energy, worlds in balance with their own brutal realities. They remind us of our profound isolation and our incredible luck. Our blue marble, with its gentle temperatures, its protective atmosphere, its liquid water oceans, is the profound outlier. It is the strange world, the rare and quiet sanctuary in a cosmos that is largely vast, cold, violent, and indifferent. The true haunting feeling comes not from the storms of glass or the rains of rock, but from the scale of it all. These terrifying planets are everywhere. For every world like ours, there are likely thousands, millions more like the ones we have seen. They are the norm. We are the exquisite, fragile exception, drifting on a pale blue dot in the immense, silent, and beautifully terrifying cosmic ocean. So, let the silence settle around you once more. Let the darkness be a comfort. And remember, out there in the quiet, the universe continues its work, building wonders and horrors beyond our wildest dreams. The silence that follows this contemplation is not empty. It is filled with the faint imagined echoes of these distant cataclysms, a cosmic background hum of perpetual silent violence. Let us delve deeper into the nature of these alien atmospheres, for they are often the source of a world's particular nightmare. Consider a gas giant not unlike Jupiter, but orbiting perilously close to its star. On such a world, the upper atmosphere is not a placid layer of clouds, but a region being slowly boiled away into space. The stellar wind, a relentless stream of charged particles, acts like a cosmic blowtorch, stripping away the planet's gaseous envelope molecule by molecule. You could witness the slow, astronomical-scale death of a world, a perpetual mist of atmospheric material streaming into the void, forming a tenuous, glowing tail that stretches for millions of miles. The planet is perpetually bleeding its essence into the darkness, a gradual and inescapable dissipation that will continue for eons until perhaps nothing remains but a barren, scorched core. It is a form of violence, not of explosion, but of erosion, operating on a scale and time frame that dwarfs human comprehension, a quiet, relentless leaching of a world's soul. Now, envision a planet trapped in a gravitational dance with not one, but two stars. A circumbinary planet orbits both members of a stellar pair. The sky on such a world would be a source of constant, unsettling change. Two suns of possibly different colors would rise and set in complex, unpredictable patterns, casting ever-shifting double shadows. For parts of its long year, the planet might bask in the light of both stars, suffering under a relentless, double-barreled assault of radiation and heat. Then, as it moves, one star might eclipse the other, plunging regions into a sudden, profound twilight, only for the hidden star to re-emerge with a glaring burst. The gravitational tides from two massive bodies would constantly stress the planet's interior, likely fueling extreme and perpetual volcanism. The very ground would be restless, heated and kneaded by the conflicting pulls of its two suns. The surface could be a cracked and fractured plain, continually spewing forth lava, while the sky above tells a confusing story with its two moving lights. It is a world without constancy, without a single, reliable anchor in its heavens, subject to the whims of a complex gravitational melody that permits no peace. There are also worlds where the very concept of a surface becomes ambiguous, a transition not from land to air, but from gas to a strange degenerate matter. Imagine descending into the atmosphere of a super Jupiter, a gas giant dozens of times more massive than our own. The beautiful banded cloud tops would give way to deepening layers of incredible pressure and heat. The colorful ammonia and water clouds would be left far above. As you descend further, the light from the distant star would fade, swallowed by the thick, hot gases. The atmosphere itself would gradually thicken, becoming a soupy, supercritical fluid. There would be no clear boundary, no moment where you land. Instead, the hydrogen and helium around you would simply get denser and hotter until they transition into exotic states like liquid metallic hydrogen, a form of matter that is an electrical conductor, swirling with immense currents. You would be sinking into an endless, dark, electrically charged ocean, where pressures are so great that matter itself is compressed into forms unknown on Earth. It is a world with no bottom, only an infinite crushing descent into a realm where physics becomes strange and forbidding, a perpetual fall into the heart of a perpetual storm. We must also consider the chilling possibility of planets orbiting the remnants of dead solar systems. After a star like our Sun ends its life, swelling into a red giant before shedding its outer layers, it leaves behind a white dwarf, a hot, Earth-sized ember of degenerate matter. Planets that survived the red giant phase would now orbit this dense, fading cinder. The light from a white dwarf is stark and unforgiving, offering little warmth. A planet in the now cold, habitable zone would be a frozen, airless rock, illuminated by the pale, ghostly light of a stellar corpse. Any former atmosphere or oceans would have been boiled away during the star's death throes. The landscape would be one of absolute sterility, a bone-white or charcoal-black terrain under a black sky dominated by a small, intensely bright pinprick. It is a tomb of a world, orbiting a tomb of a sun, a system that has passed through its vibrant life and into a permanent, cold quiet. The horror here is one of absolute finality, a quietus that has already settled in, leaving behind only relics under a dead light. Then there are the worlds, sculpted not by the gentle accumulation of dust, but by colossal impacts. Imagine a planet that, in its early history, suffered a collision so titanic that it completely shattered its original form. The debris from this apocalyptic event might have coalesced into a new world, or perhaps a pair of worlds forever bearing the scars of their violent birth. The surface could be a global patchwork of different geological regimes, a chaotic jumble of rock types and minerals fused together in the heat of the impact. The mantle might be uneven, the core misaligned, leading to a magnetic field that is patchy and weak, offering little protection from stellar radiation. The entire planet might still be seismically active, shuddering with the deep tectonic echoes of that ancient, formative violence. It is a world born from catastrophe, its very geology, a chronicle of a single, universe-shattering moment of chaos, a permanent testament to the destructive forces that also build. As we push our imagination to the very limits, we can ponder the theoretical extremes. What of a planet orbiting? Imagine you are floating, weightless, perfectly still. There is no up or down, only a gentle sense of drifting. The familiar sounds of the world have faded away, replaced by a profound and peaceful silence. And before you, suspended in an endless velvet dark, is a single beautiful point of light. Our home, the Earth. From here, it looks like a delicate blue and white marble, wrapped in a shimmering veil of atmosphere. It is both everything we know and just one small world among many. Tonight, let that feeling of quiet wonder carry you. Let your mind drift away from the surface and join me on a slow, gentle journey. We will travel from our warm, familiar sun, past worlds of rock and ice and gas, to the very edges of our celestial neighborhood. This is not a voyage of speed, but of observation, a peaceful tour through our solar system where we can simply look and wonder and rest. So take a deep, slow breath. Feel yourself becoming lighter. The gentle pull of our planet is releasing you. And as you look out into that star-filled darkness, we begin our journey from the very center of it all. Our sun is not just a light in the sky. From here, as we drift closer, it is a presence, a vast, gentle furnace of warmth and light. Its surface is not solid, but a luminous ocean of churning plasma, rising and falling in great slow waves. From this distance, you can feel its energy not as a harsh glare, but as a constant, soothing radiance on your skin. It is the heartbeat of our solar system. Every planet, every piece of dust, every comet that graces our night sky, all of them dance to the slow, steady rhythm of this star's gravity. It holds our entire family of worlds in its gentle, unwavering embrace. And as we turn from its comforting glow, we set our course for the first and smallest of the planets that circle it. A world that stays so close to the sun, it feels its warmth more intensely than any other. Mercury emerges from the sun's brilliant halo, not as a world of color, but of shadow and ancient light. It is a gray, cratered sphere that looks much like our own moon. There is a deep silence to this place, a stillness that feels older than time itself. As we drift down towards its surface, we see a landscape sculpted by unimaginable patience. Countless craters, large and small, tell a story of impacts that happened billions of years ago. The ground is covered in a fine gray dust, and without any air to blow it, every footprint, every mark, would remain perfectly preserved for eons. The sky above is a profound and starry black, even in the middle of the day. And there, fixed in that blackness, hangs our sun. It appears enormous here, nearly 3 times the size we see from Earth. But from this silent vantage point, it does not feel threatening. It feels like a watchful, brilliant guardian. The heat on the sunlit side is immense, but here in our imagination, we simply observe it. We notice the long, sharp shadows cast by crater rims, creating patterns of stark light and deep darkness. This is a world of extremes, where the line between day and night is a stark frontier. But for all its harshness, there is a serene beauty in Mercury's simplicity. It is a quiet, rocky testament to the early days of our solar system, a memory held in stone. And as we push gently away from its dusty plains, we look back to see it shrinking once more, a tiny gray pearl orbiting its brilliant star. Our journey continues inward, towards a world that from a distance shines with a soft, creamy light. It is the brightest object in our night sky after the moon, often called our sister planet. But as we approach Venus, we begin to see that this sister world is shrouded in mystery. A thick, unbroken layer of clouds wraps the entire planet, reflecting the sunlight so brilliantly that it gleams like a jewel. There are no surface features visible from here, only a smooth, luminous blanket of white and yellow. This cloud layer is not made of water vapor like Earth's, but of sulfuric acid, creating a permanent global haze. As we descend into this cloud deck, the sunlight begins to diffuse into a dim yellowish glow. The silence is different here. On Mercury, it was the silence of emptiness. Here, it is the silence of profound pressure, of a heavy, still atmosphere. The clouds are thick and soupy, and visibility drops to just a few meters. It feels like floating slowly through a warm, dense fog that has persisted for hundreds of millions of years. The pressure here is crushing, equivalent to being nearly a kilometer underwater on Earth. And the temperature is astonishingly uniform and hot, enough to melt lead. This is a world governed by a runaway greenhouse effect, where the thick atmosphere traps the sun's heat and never lets it go. If we could somehow pass through those endless clouds and see the surface, we would find a landscape of rock baked under an orange sky. Vast plains of volcanic basalt, twisted mountain ranges, and countless volcanoes, some of which may still be active. The ground would glow with a dim, hellish light filtered through the clouds above. But we do not need to go there to appreciate Venus. There is a lesson in its clouds. Venus shows us a possible path a world can take, a reminder of the delicate balance that makes our own blue planet so rare and so precious. As we rise back up through the perpetual cloud layer, breaking into the sunlight once more, we leave Venus behind as that brilliant, unreadable star, a beautiful enigma, forever wrapped in its own veil. And now, we drift back toward the light. Growing larger in our view is the most beautiful sight we have yet encountered, a swirl of blue and white and brown, dotted with green, wrapped in those delicate swirling white clouds. It is Earth. Coming home, even just in passing, fills the mind with a deep and quiet awe. From here, you can see the dynamic nature of our world, the great blue oceans, the brown and green patches of continents, the ever-changing dance of weather systems across the globe. That thin, bright blue line at the edge is our atmosphere. It looks so fragile, so impossibly thin, and yet that tiny shell of air is everything. It is the blanket that keeps us warm, the shield that protects us, the very breath of every living thing we have ever known. We watch as the Terminator line, the boundary between day and night, slowly sweeps across the planet. On the night side, you can see the faint scattered glow of human cities, like tiny embers clinging to the dark. It is a humbling and peaceful sight. Our entire history, every joy and every sorrow, every person who has ever lived, has happened on that one small, beautiful sphere drifting in the vast dark. We linger here for a moment, in silent appreciation, before turning once more to the depths. Moving outward now, we pass the orbit of our home and set our sights on a rusty red dot. Mars has captivated the human imagination for centuries, the planet of war, of mystery, of potential. As we grow closer, its rusty hue becomes clearer, painted across the entire planet by iron oxide, the same compound that gives rust its color. This is a world of gentle deserts. The sky here is not black, but often a pale pink or butterscotch color, filled with fine dust. The air is whisper-thin, barely there at all. The landscape is one of profound stillness. We see the largest volcano in the solar system, Olympus Mons, a shield volcano so wide its base would cover the state of Arizona. It is not a jagged peak, but a gentle, massive slope rising so gradually you might not even realize you are climbing it. Nearby, we find Valles Marineris, a canyon system that dwarfs our own Grand Canyon, a scar across the face of Mars that speaks of ancient geological stresses. If you stood on the surface, the wind would be a faint, almost inaudible sigh, just enough to lift the fine red dust into gentle, slow-moving clouds. The sunlight is weaker here, giving everything a softer, dimmer look. At the poles, great caps of water ice and frozen carbon dioxide, dry ice, expand and contract with the seasons. There is evidence everywhere of a wetter past. Dried up river channels, lake beds, minerals that only form in water. Mars feels like a world that has gone quiet, a place where great processes have slowed to a near standstill. It is not a dead world, but a sleeping one, holding its secrets in the cold, red dust. There is a profound peace in its barren beauty, a silence that encourages reflection. As we leave Mars behind, its red glow fading against the star field, we are moving now into a new realm. We are about to cross a threshold, leaving behind the small, rocky inner planets and entering the kingdom of the giants. The first sign is not a planet, but a vast, sprawling field of rocky debris. This is the asteroid belt, a region between Mars and Jupiter filled with millions of objects, from dust-sized particles to the dwarf planet Ceres, which is nearly 600 miles across. From within, it is not a dangerous maze as sometimes imagined. The asteroids are so widely spaced that drifting through this region, you would rarely see one. They are lonely mountain ranges floating in space, most of them dark and irregularly shaped, slowly tumbling as they orbit the sun. They are the leftover building materials of the solar system, the pieces that never came together to form a planet. There is a quiet, ancient dignity to them. Each one is a time capsule, a preserved fragment of the solar system's very first days. We pass by them slowly, these silent, rocky sentinels, and as we do, a new presence begins to dominate the sky ahead. It starts as a bright, creamy star, but it grows and grows until it is no longer a point of light, but a vast, striped sphere filling your vision. Jupiter, the king of the planets. It is impossible not to feel a sense of awe. This is a world so large that over 1,000 Earths could fit inside it. It has no solid surface to stand on. Jupiter is a gas giant, a colossal sphere of mostly hydrogen and helium, with a core of perhaps molten rock and metallic hydrogen. What we see is its upper atmosphere, a breathtaking tapestry of swirling clouds. Great bands of white, tan, orange, and brown flow parallel to its equator, moving at different speeds. Within these bands, storms swirl and dance. The Great Red Spot, a storm larger than Earth that has raged for at least hundreds of years, is a deep, rusty oval slowly turning in the southern hemisphere. The clouds themselves move in beautiful, complex patterns, flowing in streams and eddies, rising and sinking in vast, slow motion. As we drift closer, we would be enveloped by the top layers of its atmosphere. The feeling would be of descending into an endless, turbulent sky. The colors would deepen around you. The winds, composed of the same gases that make up stars, would howl with unimaginable force, though from within our peaceful journey, we simply observe their power. Lightning flashes, larger than continents, illuminate deep cloud layers. The pressure would increase rapidly, crushing and heating the gases until they behave in strange, fluid, metallic ways. Jupiter is less a planet and more a failed star, a body that gathered immense mass but never quite ignited the fusion fires in its core. It radiates more heat than it receives from the sun, glowing with a gentle internal warmth from its own slow contraction. And around this giant dances a miniature solar system of its own, at least 95 moons. We see the four largest, the Galilean moons, as distinct worlds themselves. Io, a yellow-orange moon dotted with active volcanoes, painting its surface in sulfurous colors. Europa, a smooth white sphere cracked with dark lines, hiding a global ocean of liquid water beneath its icy shell. Ganymede, larger than the planet Mercury, and Callisto, a dark, heavily cratered world. Jupiter is a system unto itself, a complex, dynamic, and majestic center of gravity and motion. Its presence is calming in its sheer scale, and the slow, predictable dance of its storms and moons. We pull away from its immense gravitational embrace, its banded face slowly shrinking, and set a course for the next jewel in the solar system's crown. With its stunning pale yellow hue and magnificent system of rings, Saturn is perhaps the most iconic sight in our celestial neighborhood. As it grows in your view, its beauty is almost dreamlike. The rings, made of countless particles of ice and rock ranging from dust grains to house-sized boulders, catch the sunlight and glow with a soft, ethereal light. They are incredibly thin, only about 30 feet thick in most places, but they stretch over 175,000 miles from end to end. From a distance, they appear as solid, smooth disks, but closer up, you can see they are made of thousands of individual ringlets, like the grooves on a vast cosmic record. There are gaps in the rings, cleared by the gravitational influence of Saturn's many moons. The Cassini division is a prominent dark band, a space of relative emptiness between the brighter rings. The planet itself is another gas giant, similar in composition to Jupiter but with a softer, more pastel appearance. Its cloud bands are subtler, fainter yellows and golds. The winds here are also incredibly fast, but the overall feeling is one of serene grandeur. Saturn is the lightest planet for its size. If you could find an ocean large enough, it would float. And just like Jupiter, it is accompanied by a host of moons. Over 140 of them. Titan is the largest, a world larger than Mercury, shrouded in a thick orange atmosphere of nitrogen and methane. It has rivers and lakes, not of water but of liquid methane and ethane, flowing across a landscape of water ice. Another moon, Enceladus, is a small, bright world of pure ice. From its south pole, geysers erupt, spraying water vapor and ice particles into space, a clear sign of a subsurface ocean. Saturn's system is a place of quiet magic. The silent, graceful arcs of the rings, the soft glow of the planet, the mysterious moons hiding their secrets. It feels like a place from a gentle dream. We drift for a time just outside the rings, watching the play of sunlight on ice before moving on, farther from the sun's warmth than we have ever been. The next world we encounter feels like a shift in the universe's palette. Uranus appears as a smooth, featureless disk of pale cyan, a soft blue-green color. This comes from methane in its upper atmosphere, which absorbs the red light from the sun and reflects the blue and green. Uranus is an ice giant with a composition different from Jupiter and Saturn. It has a small, rocky core, surrounded by a deep, slushy mantle of water, ammonia, and methane ices, and an outer atmosphere of hydrogen and helium. What makes Uranus truly unique is its tilt. Its axis of rotation is tilted so extremely that it essentially orbits the sun on its side, rolling along like a ball. This means its poles get 42 years of continuous sunlight, followed by 42 years of darkness during its 84-year orbit. As we approach, we look for cloud features, but the atmosphere appears profoundly calm and uniform, a serene, unbroken sea of pale blue. Deeper down, winds do blow, and there may be storms, but from the outside, Uranus presents a face of perfect, tranquil stillness. It has a faint ring system, dark and difficult to see, and a collection of small, dark moons. There is an elegant, quiet mystery to this world. It feels detached, serene, and profoundly cold, drifting on its side in the outer solar system with a dignified silence. Its sibling in the realm of the ice giants is Neptune. As we draw near, the color deepens from Uranus's pale cyan to a rich, deep azure blue. This, too, is from atmospheric methane, but here the color is more intense, a vivid sapphire against the black of space. Unlike the calm face of Uranus, Neptune's atmosphere is dynamic. Even from a distance, you can see great dark storms and bright white clouds of methane ice crystals racing across its face. The most famous of these was the Great Dark Spot, a storm similar to Jupiter's Great Red Spot, though it has since faded. The winds on Neptune are the fastest in the solar system, reaching supersonic speeds. Yet from our distant, peaceful vantage, these storms look like slow, graceful swirls in a deep blue painting. Neptune radiates internal heat, like Jupiter and Saturn, causing its weather systems to be active and ever-changing. It has a faint, clumpy ring system and a fascinating moon, Triton. Triton orbits in the opposite direction of Neptune's rotation, suggesting it was a captured object from the distant Kuiper Belt. It is geologically active, with geysers of nitrogen gas erupting from its icy surface. Neptune feels like a world of deep, contemplative beauty. Its intense blue color is soothing, and the slow dance of its high-altitude clouds has a hypnotic, peaceful quality. We are now very far from home. The sun from here is just a very bright star, no longer a disk, but still the brightest point in the sky. Its light is weak, but its gravitational hold remains. Our journey does not end with Neptune. We venture farther into a region of growing darkness and cold. We enter the Kuiper Belt, a vast, disc-shaped region beyond Neptune filled with icy bodies. This is the home of dwarf planets, including Pluto. For a long time, we saw Pluto as just a faint point of light. But as we approach, it resolves into a small, complex world. It has a heart, a vast, bright plain of nitrogen ice shaped like a heart, now officially named Tombaugh Regio. The surface is a patchwork of terrains, dark, cratered regions of methane-stained water ice, bright plains of nitrogen, and mountains of water ice that stand as hard as rock at these temperatures. Pluto has a thin, hazy atmosphere of nitrogen, methane, and carbon monoxide that freezes and falls to the ground as snow when Pluto is farther from the Sun in its long elliptical orbit. It has a large moon, Charon, so big relative to Pluto that they orbit a common point of gravity between them, forever locked in a graceful dance. From the surface of Pluto, the Sun is merely a piercingly bright star in a perpetually black sky. The landscape is frozen in time, a testament to the slow, cold processes of the outer solar system. There is no sound, only an absolute deep freeze silence. Yet in its varied terrain and surprising geology, Pluto feels alive with history. It is a small, distant world that reminds us that wonder exists even in the farthest, coldest reaches. And still, we can drift farther. The Kuiper Belt extends outward, and beyond it lies a theoretical shell of icy objects called the Oort cloud. This is the true frontier of our solar system. From here, the Sun is indistinguishable from the brighter background stars. Its light is a memory. Its gravity is just a faint whisper, still holding comets in orbits that take millions of years to complete. This region is not empty. It is populated by trillions of icy planetesimals, the pristine leftovers from the solar system's formation. Occasionally, the gravity of a passing star nudges one of these ice chunks inward, and it begins a long, slow fall toward the inner solar system, warming as it goes, developing a glorious tail of gas and dust, becoming a comet that graces our skies for a brief, beautiful time. We are at the very edge of the sun's influence. The space between stars, the interstellar medium, lies ahead. Our solar system, from this perspective, is just a tiny island of light and matter in an unimaginably vast ocean of dark, quiet space. As we begin our long, slow drift back inward, we carry with us the memories of these worlds, the silent, cratered plains of Mercury, the shrouded, mysterious glow of Venus, the vibrant, living blue of Earth, the rusty, quiet deserts of Mars, the majestic banded might of Jupiter, the serene, ringed elegance of Saturn, the tilted, pale blue calm of Uranus, the deep, stormy azure of Neptune, and the small, complex heart of Pluto out in the frozen dark. Each one is unique. Each one is a world with its own story, its own character, its own place in the gentle gravitational dance orchestrated by our sun. We are now returning to that pale blue dot, growing larger once more, seeing it from this journey's end, with the experiences of all these other worlds in our mind, makes it seem even more precious, more beautiful, more fragile. It is not just a planet. It is our garden, our cradle, our home in the cosmic dark. The only place we know that has that delicate blanket of air, those vast, life-giving oceans, that vibrant green biosphere. All the wonders we have seen, the gas giants, the ice rings, the distant dwarf planets, none of them have what we have right here. It is a humbling and deeply calming thought. As you feel your mind settling, your breathing slow and steady, hold that image of our solar system in your thoughts, not as a diagram, but as a living, breathing neighborhood, a family of worlds, each on its own path, each turning in its own time, all connected by gravity and sunlight. There is no rush out there. Orbits are measured in years, in decades, in centuries. Storms last for lifetimes. Craters hold their shape for billions of years. It is a realm of immense, patient, peaceful cycles. You are here on this one special world, under the same night sky that has inspired wonder since the first human looked up. The planets you learned about tonight are still there, right now, moving along their silent paths. Jupiter is still turning, its great red spot slowly spinning. Saturn's rings are still catching the sunlight. Neptune's deep blue atmosphere is still swirling with storms you cannot see. And here you are, safe, resting, a part of this same vast, interconnected system. You are made of stardust, riding a pale blue planet around a gentle star in the quiet suburbs of a spiral galaxy. Let that feeling of connection be your anchor, a deep, quiet peace that comes from knowing your place in the cosmos. Not a small place, but a connected one. You are a part of this grand, slow, beautiful story. So, as you drift toward sleep, let your thoughts drift among those quiet worlds. Imagine floating past the rings of Saturn or watching the soft clouds of Jupiter from afar. There is no destination, only the gentle journey. The universe is vast and peaceful and full of quiet wonder. And you, here in your bed on Earth, are a cherished part of it all. Let the silence of space, the slow dance of the planets, and the gentle light of distant stars carry you into a deep, restful, and dream-filled sleep. Good night.
The universe is unimaginably vast. There are hundreds of billions of stars in our galaxy alone, many of which are far older than our sun. It seems highly probable that someone out there must be looking back at us, and yet, no matter how closely we listen or observe, we've heard only silence. This puzzling contradiction is known as the Fermi paradox. It poses a simple yet persistent question. If the cosmos is teeming with opportunities for life, then where is everyone? Consider this. In the grand 4.5 billion year history of the Earth, our civilization is relatively newborn. Meanwhile, the galaxy around us is ancient. If an extraterrestrial civilization had arisen even a few million years before us, a mere blink of cosmic timescales, it could have already spread across many stars. Physicist Enrico Fermi famously pondered this in 1950, asking over lunch, "Where is everybody?" A question that continues to echo in scientific circles. Decades later, we're still searching for an answer. Have advanced extraterrestrials ever existed? And if so, why haven't we encountered them? Over the years, scientists and thinkers have proposed numerous hypotheses to resolve the Fermi paradox. Each offers a perspective on a possible cosmic truth, some hopeful, some grim. Let's explore some of the most fascinating scenarios, traveling through the ideas of danger, isolation, and rarity in search of reasons for the silence of the stars. Our first stop is a place of danger and silence, the dark forest. While this idea originates from science fiction author Liu Xinjin, it resonates as a chillingly plausible reality. Imagine the universe as a vast, ancient forest at night. Each civilization is like a hunter, armed, wary, and moving stealthily among the trees. They know that others might be out there, but revealing their presence by making noise could be deadly. According to the dark forest hypothesis, intelligent civilizations remain silent and hidden out of fear. Any form of life that announces itself risks drawing the attention of another, one that might see it as prey or a threat. In Liu's eerie analogy, the cosmos is filled with silent, paranoid beings, each stalking like a ghost in the darkness. No lights, no signals, only the hush of hunters trying not to be hunted. Why such fear? Because in this dark forest, survival is the only rule. Resources are limited, and any other civilization is an unknown, its intentions and capabilities unclear. Even the weakest seeming culture could suddenly leap ahead with new technology and become a mortal enemy. The safest strategy is to assume the worst. If you hear another in the forest, eliminate them before they eliminate you. So everyone stays quiet, erasing any traces of their existence. This hypothesis flips the Fermi paradox on its head. Perhaps the great silence isn't because we're alone, but because the galaxy is full of life forms too terrified to announce their presence. If the dark forest is real, an unsettling thought arises. In searching for friendly extraterrestrials, the simple act of shouting, "We are here," could be the very thing that leads to our doom. However, maybe silence is not just out of fear. It could be the result of something even worse. Not hiding, but extinction. In the cold vacuum of space, another grim possibility lurks. What if we haven't heard from extraterrestrials because they're all gone, perhaps wiped out by an unstoppable threat? This is the Berserker hypothesis, perhaps the darkest explanation of all. It suggests that civilizations across the galaxy aren't silent by choice, but forced into silence. The idea gets its name from fictional Berserker probes, deadly, self-replicating machines programmed to seek and destroy life. Imagine an automated killer, a robotic virus, spreading from star to star. Such probes, often referred to as von Neumann probes, after the mathematician who theorized self-replicating machines, could multiply exponentially and sweep across the galaxy. If even one advanced species were to unleash something like this out of paranoia or malice, it could mean the doom of all others. Astrophysicist David Brin once remarked, "It need only happen once for the results of this scenario to become the equilibrium conditions in the galaxy." In other words, a single outbreak of berserkers in the distant past could have left the galaxy silent and lifeless. According to this hypothesis, the Great Silence exists because whenever life becomes loud enough to become noticed, say by broadcasting radio signals or launching space missions, berserker probes detect it. Then, like cosmic predators, they descend and erase that life before it can spread. The universe in this grim scenario might be littered with the ruins of civilizations that reached for the stars only to be extinguished. If this is true, we are lucky, or perhaps only lucky for now, that we haven't yet attracted the attention of something predatory lurking out there. Brin once summarized this chilling idea with a warning. If the berserker scenario is correct, we will not find a single intelligent life form out there, including, one day, ourselves. This fear is valid. Our SETI signals, our television broadcasts leaking into space, could one day serve as a beacon leading to our own destruction. And yet, if we're still here, perhaps the worst hasn't happened. Or maybe something or someone is actively protecting emerging civilizations like ours. What if the silence is not enforced by killer machines, but by a form of cosmic caretaking? Let's consider another scenario, slightly less terrifying. What if advanced aliens are indeed aware of us, but prefer to remain hidden, much like zookeepers behind a one-way mirror? This idea is known by the playful name, the space zoo hypothesis. It suggests that we humans are essentially an exhibit or an experiment being observed by higher civilizations that have agreed not to interfere with our development. In other words, we haven't encountered aliens because we aren't supposed to. In this hypothesis, Earth is akin to a wildlife reserve or a protected island tribe. Think of the uncontacted people of North Sentinel Island in the Bay of Bengal. They live in isolation while the modern world watches from a distance, respecting their wishes and legal protections that ensure that they're left alone. Similarly, advanced aliens might enforce a strict non-intervention policy toward developing civilizations like ours. This could be driven by ethical concerns, like the belief that young species should find their own path without external influence, or simply a form of cosmic anthropology, allowing them to observe us to understand how intelligent life evolves naturally. The zoo or space quarantine analogy implies that evidence of alien existence might surround us, but it is deliberately hidden. We scan the skies and see nothing because we're looking at a one-way mirror. They see us, but we don't see them. This is almost reassuring. Instead of a hostile jungle or an intergalactic slaughterhouse, the universe in this scenario is a vast wildlife park, managed by benevolent or at least indifferent overseers. But there's a catch. It implies the existence of some kind of galactic club with rules we don't know. And this raises another possibility. Perhaps this isn't just passive observation, but active enforcement of cosmic law. If the zoo hypothesis portrays aliens as discreet caretakers, the space police hypothesis depicts them as galactic enforcers. Imagine a highly advanced civilization, or a whole coalition, patrolling the stars and enforcing laws on any rebellious society. As soon as a civilization becomes spacefaring, or starts developing dangerous technologies, the space police arrive and lay down the law. Stay put. These are the rules of the galaxy. This idea is essentially an extension of the zoo concept, but with a more active role. Perhaps an unspoken prime directive exists in space, a term borrowed from Star Trek's non-interference doctrine, and a powerful civilization ensures its enforcement. They might prevent young species from making reckless moves, such as aggressively expanding, sending out self-replicating probes, or developing planet-destroying weapons. In a way, they could regulate behaviors that could threaten others or destabilize cosmic order. If humanity crosses a certain line, say by attempting to create an uncontrollable AI or launching a Van Neumann probe swarm, This hidden authority might intervene, and perhaps not with a friendly warning. Some theorists have joked that the police might simply send an asteroid our way as a harsh lesson. It's a risky test. If we push things too far and nothing happens, maybe there are no vigilant guardians after all. But if they do exist, crossing that line might be the last thing we ever do. So far, there's no evidence that anyone has intervened in our affairs. No alien officers handing out fines for humanity's bad behavior. But there's a certain dramatic appeal to this hypothesis. The idea of an organized galactic community that cares enough to prevent cosmic disasters. If true, perhaps we remain unharmed, not by chance, but by design, protected until we are mature enough to join the Galactic Club. But what if, unlike all these scenarios, the simplest answer to where is everybody is there's no one out there, or at least no one capable of saying hello? Perhaps life, especially intelligent life, is exceedingly rare. Earth often seems ordinary, a typical rocky planet orbiting a fairly unremarkable star. But what if Earth is actually the winner of a cosmic lottery? The rare Earth hypothesis argues exactly this, that the emergence of complex life here required such an improbable combination of conditions that it might be practically unique in the universe. In other words, intelligent civilizations might be rare and scattered, or even one of a kind, because the odds were stacked against their evolution. Consider everything that had to happen for us to exist. We are at the perfect distance from the sun, allowing liquid water to persist. Our sun is stable, neither too hot nor too cold. We have a giant guardian, Jupiter, whose gravity deflects comets that might otherwise frequently strike Earth. We have a large moon that stabilizes our planet's tilt and seasons. Plate tectonics regulate our climate, and we've been afforded the exact right amount of time for life to evolve from microbes to multicellular organisms. Even rare events, like ice ages and mass extinctions, might have triggered evolutionary leaps at the right moments. It's a long list of lucky coincidences that, when combined, could be extraordinarily rare. Paleontologist Peter Ward and astronomer Donald Brownlee, who popularized this hypothesis, noted that microbial life might be common. Microbes are hardy and can survive extreme conditions, but the transition to complex animal-like life may require a stroke of luck that happens only rarely. If advanced life needs a planet exactly like Earth, with all these special factors in place, it's no surprise that we don't see alien neighbors. We might literally be the only technological civilization for galaxies around. This scenario is sobering in its own way. The silence around us might not be due to fear, hostility, or regulations. It could simply be that no one else was lucky enough to make it this far. Earth could be a rare oasis in a sterile cosmos. If that's the case, then an immense responsibility falls upon us. In a sense, we carry the torch of consciousness for the entire galaxy. It's a call to cherish and protect the life we have, knowing how fleeting and improbable it may be. And yet even the rare Earth hypothesis doesn't close the case completely. After all, the universe is vast. Even rare events can happen multiple times with enough cosmic dice rolls. Perhaps intelligent life emerges elsewhere, only to encounter obstacles it cannot overcome. This brings us to a profound concept that looms over any discussion of cosmic loneliness: the Great Filter. The Great Filter is not a single hypothesis, but rather an overarching idea. It suggests that on the path from simple life to an advanced spacefaring civilization, there is a stage that is extremely difficult to overcome, so difficult that almost no one makes it past. The filter might be behind us. Perhaps the leap from non-life to life is so rare that it's only happened once in our galaxy, and we have already passed that threshold. Or the filter might be ahead, an obstacle that nearly all civilizations reach but fail to surpass. If that's the case, we've yet to face the greatest challenge. Economics professor Robin Hanson, who coined the term, described the Great Filter as a probabilistic barrier. a series of highly improbable steps in evolution or development. For example, it may be extraordinarily unlikely for life to evolve from simple single-celled organisms to complex multicellular ones, or for intelligent animals to develop technological civilizations. If even one of these steps is astronomically improbable, it would eliminate the vast majority of life forms before they ever reach the stars. Philosopher Nick Bostrom put it succinctly: if we find the cosmos empty, it might mean almost no one can get all the way to detectable spacefaring status. Something stops them. A chilling implication. If we discover primitive life elsewhere, such as fossilized bacteria on Mars or microbes on Europa, it would suggest that the early stages of life are common. And this would mean the great filter is most likely ahead of us. A rare, fatal step may lie somewhere in the future, waiting to be faced. And we must ask, what could this future filter be? Nuclear war? An AI gone rogue? Environmental collapse? One candidate that scientists soberly consider is a pandemic, whether natural or engineered. We've already seen firsthand how quickly a new virus can spread across the world. Even with modern medicine, a pandemic can claim millions of lives and destabilize civilization. Now imagine a disease far more lethal, or a genetically engineered superpathogen. It's not surprising that an advanced society could, either by accident or intent, create something it cannot control. The renowned physicist Stephen Hawking warned that humanity's growing technological power leads to, quote, new ways things can go wrong. And he specifically feared engineered viruses as a potential civilization-ending threat. Could a virus or a plague be the great filter that naturally limits intelligent life? Possibly. A sufficiently deadly global pandemic, breaking out before a species can colonize other worlds, could wipe out civilizations or revert it to the Stone Age. Humanity bears the scars of past plagues like the Black Death in the 14th century, which wiped out a third of Europe. One can only imagine alien worlds where successive pandemics destroyed societies before they ever sent a radio signal to the stars. Interestingly, viruses have also been an integral part of evolution itself. Astrobiologists note that viruses are widespread on Earth and may have existed since the origin of life. They drive evolution by forcing organisms to adapt. In fact, some DNA in our own genome comes from ancient viruses. Without this pressure, complex life might never have arisen. In this way, viruses play a dual role. They can accelerate the progress of life, but they can also trigger catastrophic collapse. The idea that a great filter lies ahead is undeniably frightening, but it can also be seen as a call for wisdom. If pandemics, climate collapse, or warfare are potential filters, will end. And the next great story of civilization will begin. Try to visualize a world where a year lasts only a few days. A planet so close to its star that its atmosphere is constantly being stripped away by relentless heat. These are hot Jupiters, gas giants, that defy conventional ideas about planet formation. Once thought impossible, their discovery rewrote the rules of astronomy, challenging our understanding of where and how planets can form. How do these planets survive such extreme conditions? Why do they appear in systems unlike anything we've known? Their discovery wasn't just groundbreaking, it opened the door to an even deeper mystery that continues to reshape our understanding of planetary systems. So let's begin with the event of discovering hot Jupiters in the 1990s, which revolutionized our understanding of planetary systems. Before their discovery, the dominant model of planet formation was based on our solar system. It was believed that gas giants like Jupiter could only form in the colder outer regions of a protoplanetary disk. The existence of massive, scorching planets orbiting close to their stars was not only unexpected, but posed a serious challenge to existing theories. However, a turning point came in 1995 with the discovery of 51 Pegasi b, orbiting a Sun-like star. This planet completes its orbit in just over 4 days. Such a short time period meant it was extremely close to its host star, with estimated temperatures exceeding 1,000 degrees Celsius. This discovery stunned the astronomical community. Previously, no one believed that such a large planet could form or survive so close to a star. The discovery was made using the radial velocity method, which measures the wobble of a star caused by the gravitational pull of an orbiting planet. This wobble causes tiny shifts in the star's light spectrum, a phenomenon known as the Doppler effect. Observations of 51 Pegasi showed periodic shifts in the star's spectral lines, perfectly matching the movement expected from a large, closely orbiting planet. In the following years, the radial velocity method became the cornerstone of exoplanet discovery, leading to a sharp increase in the number of detected planets. By the early 2000s, hundreds of hot Jupiters had been cataloged, each adding to the mystery of how these planets form and migrate. While radial velocity paved the way, the transit method quickly became another powerful tool. This method detects periodic dips in a star's brightness when a planet passes in front of it, partially blocking the light. The first successful detection of a transiting hot Jupiter, HD 209458b, took place in 1999. This event was revolutionary as it allowed astronomers to directly measure the planet's size and confirm its existence using independent methods. Transit observations also allowed astronomers to study the atmospheres of hot Jupiters. This became possible because certain wavelengths are absorbed as starlight passes through a planet's atmosphere during a transit, revealing the chemical composition. This method, known as transit spectroscopy, has allowed the detection of elements such as sodium, water vapor, and even exotic molecules like titanium oxide in the atmosphere of these planets. Despite the dominance of these two methods, there are other techniques that have also played a significant role in uncovering the secrets of hot Jupiters. For example, direct imaging. Despite its difficulty, this method allows astronomers to obtain real images of planets by blocking the light of the host star. Although direct imaging is mostly effective for planets located farther from their stars, it has provided remarkable insights into exoplanet atmospheres and dynamics. Another method is gravitational microlensing, which uses the gravitational field of a foreground star as a natural lens to magnify the light from a background star. When a planet orbits the foreground star, it creates a unique signal. That facilitates its detection. Although microlensing is rarely used for planet detection, it has led to several discoveries in unexpected locations. And then there is astrometry. By precisely measuring the position of stars, this method detects small movements caused by orbiting planets. Compared to other methods, astrometry is still in its infancy, but it holds great potential for studying multi-planet systems. However, the discovery of hot Jupiters also raised a number of puzzling questions. If they form far from their stars, how do they migrate inward? And why were they the first exoplanets to be discovered? We'll circle back to that. Now let's talk about another equally interesting question. For many years, hot Jupiters were considered lonely wanderers, isolated giants, whose extreme migration disrupted the very systems they inhabited. This idea stemmed from the widely accepted hypothesis that inward migration of these massive planets triggered by gravitational interactions or disk dynamics would destroy or eject nearby planets. This view appeared to be supported by observations. Early discoveries of hot Jupiters revealed systems without any detected nearby planets. The idea of hot Jupiters' isolation is rooted in the physics of planetary migration. According to models, gas giants form far from their stars, beyond the snow line, where icy materials can accumulate to create large planetary cores. However, interactions with a photoplanetary disk or other planets can force these giants to migrate inward. It was believed that this migration process, especially in its more chaotic forms, would destabilize the orbits of smaller bodies. Two main mechanisms were proposed to explain such migrations. The first is disk-driven migration. In this scenario, interactions between a planet and the gaseous photoplanetary disk lead to a gradual inward spiral. The planet's immense gravity disturbs the disk, creating density waves that transfer angular momentum, pulling the planet closer to the star. This interaction can clear material in the planet's path, potentially disrupting or halting the formation of nearby planets. The second mechanism is known as planet-to-planet scattering. In more chaotic systems, gravitational interactions between multiple gas giants can eject one planet outward while pushing another inward. The surviving inward-moving planet, now a hot Jupiter, may disrupt the orbits of smaller bodies, either accreting them or ejecting them entirely. The inward-moving planet often ends up on a highly elliptical orbit, which gradually circularizes due to tidal forces over time. It would seem that these turbulent processes explain why early observations did not detect nearby companions to hot Jupiters, reinforcing the idea of their so-called loneliness. However, despite the theoretical foundation, the myth of these giants' isolation began to crack as detection methods improved. Observations from spacecraft like Kepler and TESS revealed systems where hot Jupiters coexist with other planets, contradicting the notion that their migration universally destabilizes their surroundings. One key example is the WASP-132 system, where a hot Jupiter orbits alongside a super-Earth and an ice giant. The existence of such systems suggests that not all migrations of massive planets are destructive. In some cases, the migration path can be, quote, dynamically cool, allowing other planets to survive or even form after the gas giant's inward journey. The discovery of non-isolated hot Jupiters has led astronomers to reconsider planetary migration theories. It led to a more nuanced understanding, showing that the degree of disruption depends on several factors. One such factor is the timing of migration. If a hot Jupiter migrates early, during the gas-rich phase of the protoplanetary disk, smaller bodies may still form after its passage. However, late-stage migrations are more likely to destabilize the system. Another factor is the mass and eccentricity of the migrating planet. Heavier or highly eccentric hot Jupiters are more likely to disrupt their surroundings. Systems with lower mass giants on more circular orbits can remain relatively undisturbed. Last but not least is the matter of star-planet interactions. Gravitational interactions between the host star and its gas giant can influence the stability of nearby planetary orbits. For example, tidal forces can dampen the planet's eccentricity, reducing its potential to destabilize the system. Advances in telescopes and longer observation periods have played a crucial role in debunking the myth of isolation. For example, high-precision radial velocity data have revealed subtle gravitational effects from additional planets in these systems. Meanwhile, transit timing variations, which measure deviations in a planet's transit schedule, have helped confirm the presence of neighboring planets, even if they're too small or too distant to be directly detected. It was traditionally believed that high-eccentricity migration dominated the formation of hot gas giants, as this explained the observed lack of close companions in early systems. However, new data, including the discovery of multi-planet systems like WASP-47 and WASP-132, challenged this assumption. Observations indicate that about 12% of hot Jupiters have close neighbors, suggesting that not all high-eccentricity migrations are destructive. Understanding this allows us to conclude that migration is not a universally destructive process, but can occur under conditions that preserve or even foster the formation of additional planets. In general, hot Jupiters are not a monolithic class of exoplanets. Their discovery has revealed a surprising diversity in size, mass, and environmental conditions, with their characteristics often determined by the type of star they orbit. This diversity, ranging from lightweight gas giants orbiting cool red dwarfs to massive planets experiencing intense radiation from red giants, highlights the complexity of planetary formation and evolution. The class of the host star plays a crucial role in the formation, migration, and characteristics of gas giants. While most of them orbit sun-like stars, discoveries around other types of stars have expanded our understanding of these planets. Red dwarfs, which are smaller and cooler than the Sun, have lower luminosity and longer lifespans. Despite their lower energy output, there have been instances of hot Jupiters orbiting them, such as NGTS 1b, a gas giant nearly the size of Jupiter, orbiting a red dwarf half the size of the Sun. The existence of these planets challenges traditional formation theories, as red dwarfs are less likely to have protoplanetary disks massive enough to form such large exoplanets. When stars evolve into red giants, their outer layers expand, altering the gravitational dynamics of planetary systems. Some hot Jupiters, such as Kepler 56b, orbit these aging stars, experiencing extreme heating and tidal forces. These systems provide insight into the final stages of planetary evolution, where planets may eventually be engulfed by their expanding stars. Hot Jupiters have also been found in multi-star systems, where gravitational interactions between stars can influence planetary orbits. For example, Kepler 47c orbits within a system with 2 suns, demonstrating adaptability to such a dynamic environment. On top of everything else, the masses and size of these planets vary significantly, reflecting the diversity of their formation histories and physical conditions. Super-Jupiters such as HR 8799b are much more massive than our Jupiter, often exceeding its mass by 10 times. Their immense gravity can compress their atmospheres, leading to relatively small radii, despite their high mass. These planets provide valuable insights into the upper limits of exoplanet formation. At the other extreme are puffy hot Jupiters, such as WASP 12b, which expand to sizes far beyond what's expected for their masses. Intense stellar radiation heats these planets, causing their atmospheres to expand and lowering their density to levels comparable to cork. Some even lose mass due to atmospheric escape, forming gas tails. Additionally, small gas giants like HAT 7b lie on the boundary between Neptune-like planets and true hot Jupiters. These mini hot Jupiters challenge traditional classifications and suggest a continuum of planetary characteristics rather than distinct categories. The diversity of this class of exoplanets also extends to their internal composition and orbital properties. Planets with higher metallicity are thought to form more efficiently in protoplanetary disks, rich in heavy elements, leading to denser cores and more robust atmospheres. Orbital distances also play a role. While most hot Jupiters orbit within 0.1 astronomical units of their stars, variations in semi-major axes can affect their thermal profiles, their atmospheric retention, and even magnetic fields. The discovery of hot gas giants has changed our understanding of planetary systems and has also revolutionized the methods used to study them. The primary detection techniques, the transit method and the radio velocity method, continue to be crucial in modern astronomy. NASA's Kepler mission, launched in 2009, relied on the transit method to detect thousands of planets, revealing the extraordinary diversity of planetary systems. Meanwhile, the radio velocity method, refined by advanced spectrographs like espresso, continues to detect bodies of various sizes and masses. These tools have laid the foundation for an era of precise exoplanet science. Modern telescopes such as the James Webb Space Telescope represent a major leap forward in exoplanet research. Equipped with infrared capabilities, JWST can analyze the atmospheres of distant worlds, including gas giants, in unprecedented detail. By studying chemical composition, thermal profiles, and even cloud structures, researchers hope to uncover key insights into the formation and evolution of these worlds. Upcoming missions such as ESA's Plato and NASA's Roman Space Telescope will further these efforts by focusing on planets in habitable zones and systems around cooler stars. Together, they aim to build a complete picture of planetary diversity, from scorching gas giants to temperate Earth-like worlds. The next frontier lies in detecting the faintest signals, small planets, complex multi-planet systems, and worlds orbiting distant stars. Techniques such as direct imaging and astrometry, combined with longer observation periods, will allow astronomers to study planetary system architecture and trace their evolutionary histories. The ongoing challenge is to refine these methods, push detection boundaries, and uncover worlds that might otherwise remain hidden. The universe is vast and full of planets yet to be explored. Who knows what secrets they may hold?